Now for question 2 on our discussion. This question is called TCP calculations, and we're going to think about sizes and timer estimation. So for this first part, we ask, and let me switch to my iPad here so we can write. We ask that the MTU of some link between two N hosts is 1,260 bytes. What is the MSS? So MSS is maximum segment size. And the MTU is a property of the actual L2 restriction. It's going to be the maximum size of a packet that we can send. The MSS is going to be actual data in a packet. So really what this is asking is, given that the MTU, which here MTU is 1,260 bytes, and this packet has a TCP header and an IP header, what is the amount of data that can fit in this packet, which is the definition of the MSS, or maximum segment size? Well, the IP header here is an IPv4 header with no options. And we know that IPv headers are 20 bytes. Whoops. And a TCP header, here we have specified that it is also 20 bytes because it has no options, this particular header. And so with a 1,260 byte MTU, that leaves 1,220 bytes for the MSS. Because 1260 minus 20 gives us 1220. Okay, the next question says, when this connection starts, the sender starts with an ISN of 19. And the initial window is set to 10 packets. So using this previously calculated MSS, what ACK does the sender receive as part of the initial TCP handshake? This one we should be able to answer very quickly. In the handshake, the sender says what ISN is going to use, 19. The ACK is ISN plus 1. Which is 19, plus 1, which is equal to 20. So in the first handshake, the first ACK that's received is 20. So after that, when the data actually starts being sent, this question says, what is the first and last ACK in this initial window? Well, the window is 10 packets. So the very first ACK is going to be the ACK for the first packet, which is going to be 20, plus the number of bytes in this first packet, which is 1220. So we get 1240. So that is that first ACK that we received from this window. And the last ACK is going to be for the last packet, the 10th packet. So last ACK will be 20, which was ISN plus 1, plus 10 times the MSS. So 10 times 1220, which gets us to 12,220. Okay. Now this next part is kind of fun. Here we're going to look at estimation. And we should think just critically about why we need to estimate the timeout value. This is a good time for you to pause this video, read through the problem, and try it yourself, and then come back and watch me give the solution. The reason that we need to estimate a timeout is because the correct timeout value depends entirely on who you're talking to, how close they are, how long packets will take to make it to their destination and back. And so the way that we do this, and we give you the formulas here, is we write that the estimated timeout is the estimated RTT, so our estimate of what the average packet takes for a round trip, plus 4 times the estimated standard deviation. So we keep a running tally of our estimated deviation, standard deviation, and our estimated round trip time. And then, assuming that our round trip time looks like a normal curve, right? We're going to pick something that is 4 standard deviations. These are 4 poorly drawn standard deviations above the mean. What this tells us is like 99.9% of packets should return back, so meaning the data makes it to its destination and the MAC is received, within this window, within 4 standard deviations above the mean, above the average amount of time. So this is why this formula works. By keeping track of every packet that comes in, and every time we get a packet, an ACK for a packet that we've sent, we update our estimate for the round trip time and we update our estimate for the standard deviation. We're able to continually adjust this curve and pick the 0.4 standard deviations above the mean to use for our estimated timeout. And this works because it's pretty reasonable to assume that if the packet hasn't made it back before 4 standard deviations over the mean, we probably need to resend it. It's probably been lost. So the rest of this problem is really just applying these formulas. So the sender receives the current ACK. The time from the packet was sent to when the packet was received was 10 milliseconds. So here our old estimated RTT was 70 milliseconds. So our new estimated RTT is going to be alpha, which is 0.5, times our old estimated RTT, which is 70, plus 1 minus 0.5, which conveniently is also 0.5, of 10 milliseconds. And that gives us 40 milliseconds. Just applying the formula 1, 2, 3. Applying formula 3 here. By the way, what's up with this formula? Well, it's just a weighted average where you apply a higher weight to more recent values. And so every time you get a new value, you combine it with your old average with some proportion that is governed by alpha. And so the bigger alpha is, the more you anchor on older values, previous values that you've seen. The smaller alpha is, the bigger the contribution to this average from the new sample. Now, applying formula 2 for the estimated standard deviation, the previous standard deviation was 50 milliseconds. Beta here is 0.5, so the new standard deviation is going to be 0.5 times 50 plus 1 minus 0.5 times the estimated RTT, which here is 40 milliseconds, the new estimated RTT, minus 10 milliseconds, which is the value that we got for RTT. And when we do the math for this one, we get back actually also 40 milliseconds conveniently. And now we can apply, so this is up here, this was formula 3, this is formula 2. Applying formula 1, we can get our new estimated timeout by taking the estimated RTT, which is 40, plus 4 times the estimated deviation, which is also 40, which gives us 200. Whoops. Now for this next part 4 of our question, it's going to ask about the maximum theoretical rate of data transfer given that we have a window size of 10. So we have a window size of 10. Now this tells us that our window size of 10 packets here, right? So in bytes, how big is our window? Well, 10 packets times an MSS of 1220 gets us 1200 bytes. Okay. So now the question is, what is the maximal bandwidth for us using this previously commuted RTT? Well, assuming the RTT is, let's see, RTT up above was 40 milliseconds, or estimated RTT. Now, we have, that means 40 milliseconds. And during those 40 milliseconds, we can send up to the entire window, 12,200 bytes. So 12,200 bytes every 40 milliseconds comes out to about 30,500 bytes per second, which is our answer. Now you could ask, hey, why can't we send faster? Well, you could send faster, but then you wouldn't be filling your pipe, right? You would send faster and then you have to stop sending for a while until you get back an ACK. So you want to send at the lowest rate that still fills up the pipe, because in the pipe being the data that's inflow to the receiver and the ACK coming back. And so it takes 40 milliseconds, because that's our estimated round trip time, from the moment you first send some data to the moment that you get back an ACK, meaning your window can move forward. And so during those 40 milliseconds, you want to stretch out the total data that you can send without the window moving 40 across those 40 milliseconds, which is why we take the window size and divide it by the amount of time that the window stays still, which is the total time until the receiver sends back an ACK. And finally, for this last part of the problem, 40 milliseconds is our estimated RTT. The lowest bandwidth across this connection is 76.25 megabytes per second. So what's the smallest window that optimizes this setup? It's the same exact setup as above. It's just we have a different empty variable. And so our bandwidth is going to be 76.25 megabytes per second. So that's 10 to the 6 bytes per second. And we're going to have 40 milliseconds to send this data. In fact, we can we can make this 1000 milliseconds. And this gives us 3.05 megabytes as the window that most optimizes our connection, given that our round trip time is 40 milliseconds and the lowest bandwidth across this connection is 76.25 megabytes.